Our speaker today is Sebastian Trojanowski, who's going to tell us about neutrinos, dark sectors, and cosmological tensions.
Right, great. Thank you for having me. Thanks for having this great workshop. Also thanks for pronouncing my surname correctly, which is not that easy, I guess. I'm a particle physicist, which I should mention to begin with, but I'm trying to talk about some stuff that connects to cosmology, obviously. So please keep this in mind when I try to explain you the data, let's say, thing. But other than this, I'm going to talk about stuff that we did with William, Eleonora, Karsten, Phil, and other people. And this basically connects to neutrino dark matter interactions and, and cosmological data, of course. So first, just 2 slides, just to motivate why to even bother about neutrino dark matter interactions. I guess for some of you, I don't need to convince you. Like Julien, I guess you've been working on this for years, right? So it's natural. But generally, I would start with cosmological and particle physics perspective. So from the cosmology perspective, there is of course this tale of 2 relics. So cosmic neutrino background and dark matter, both are supposed to be relics of the very early universe. And in both cases, we actually cannot detect it. I mean the relics. Of course, we detect neutrinos, but at higher energies, not the relic ones. So of course, this is a bit puzzling, right? But we still see their profound impact on cosmology. That impacts, of course, the matter power spectrum, CMB data, and so on. In both cases. So it's natural to ask, since they were very abundant in the very early universe, whether the connection between them could be actually stronger beyond gravity and how this could impact the cosmology and observations. Then, of course, there are tensions. There's multiple tensions, and you know this much better than me, including the one directly related to the neutrino sector, at least that seems to be, like the neutrino mass tension that Julien was talking about. So we seem to have this tension between the upper bound from cosmology and the lower bound from neutrino oscillation experiments. That, of course, is subject to various uncertainties in modeling and so on. So it's not like a fixed thing. But in principle, that's another hint that maybe something's going on in this neutrino sector in the cosmology. Hopefully, we are not dealing with neutrino-less universe. So I'm going to talk about stuff that contains neutrinos in the universe. And then the other thing is that neutrino dark matter interactions can just simply have observable impact. So it's the cosmology is a good testing ground for these interactions. So this impact can be large enough to basically found bounds and constrain these models, potentially see hints of these interactions. All right, so then from point of view of particles, then there is many motivations that one could do, but 2 that are most obvious. One is of course neutrino oscillation itself. So this phenomenon that goes beyond the standard model makes neutrinos a very natural candidate to basically consider them as a window to new physics and potentially to dark sectors. So it's a very natural thing to ask whether they can also connect to dark matter. And then another thing is that they can also quite naturally save the thermal dark matter paradigm, which is kind of a WIMP miracle thing, if you know. So in the case of WIMP, so weakly interacting massive particles that could serve as dark matter, there is this well-known story of the thermal freeze-out. So these particles were in thermal equilibrium in the very early universe. And then they started efficiently annihilating without being reproduced in the thermal plasma. But at some stage when the universe expanded enough, this annihilation ceased to be effective, and the comoving number density of these particles basically froze out. So we call this thermal freeze-out. And there was this nice coincidence that was noted decades ago that for the WIMPs of the mass around the electric scale and the weak scale coupling, you can get precisely correct relic abundance of dark matter. And then there were multiple extensions of these for various models and variations, but basically relying on the very same picture of the thermal freeze-out. And this is now under a strong scrutiny from observations. So people have spent like several decades trying to test these in various experiments, including direct detection, indirect detection, and other searches. And in many cases, we've been able to rule out this possibility. It's not completely ruled out yet. And one possibility that is still there is that if dark matter couples to neutrinos predominantly, and the neutrino annihilation to neutrino is responsible for this freeze out, then it is this place where current bounds are relatively weak, so we can safely rescue this nice picture. And the picture is nice because this freeze out, this value of the relic abundance of dark matter is completely insensitive to whatever happened in the early universe, like inflation and so on. So that's why the people very much liked it. And here you see the bounds on annihilation cross-section on neutrinos, and the thermal target, which is this line, which hopefully you can see here, and the bounds are here. So we are still in most ranges orders of magnitude away from probing it. So there is a lot of space for thermal dark matter. By the way, I know the questions are at the end, but if there are any questions in the middle, feel free to ask, of course. Like this. Like this? Okay, yes, yes. Yeah, I realized. Maybe I can try. All right. So now there is many effects in which neutrino dark matter interactions can affect cosmology, and Julian in particular, and many other people have been studying this for years. So here I just mentioned two things that will be kind of relevant to what I'm going to talk about, which is the neutrino drag. So basically, dark matter can be trapped in oscillation force and then can dump high multiple tails of the CMB spectrum. Here's the plot from our paper that was nicely made by William, I think, in the past, that shows that how the high multiple spectrum of CMB can be bumped, suppressed, depending on the strength of this interaction. This parameter, I'll come back to it in a second, but basically the higher the number it is, the less negative, then the stronger is the interaction, and you see the suppression. Then another thing that I'm going to talk about is about weak lensing. So of course, at a bit larger scales, you can also, but not that much, you can also expect that this interaction can suppress the matter power spectrum, and then this can induce impact on things like cosmic shear. And this is from another paper that we did recently published in Nature Astronomy, basically data point from DESY3 at that time. That was the relevant data set versus the different versions of the interacting neutrino dark matter model. So I will start with presenting some stuff for neutrino dark matter interactions, how they basically look in the data, and then I will go beyond what is typically done in the literature and try to convince you that what is typically done is an incomplete picture, sort of, in terms of particle physics background, at least. So what is typically done in the literature, but not always, of course, but that's a typical assumption, is that the cross-section, so the interaction rate basically between neutrino and dark matter is constant, and by constant I mean it's temperature independent. So basically it's the same across temperatures in the early universe or across redshift ranges. That's a simplifying assumption, but it's very, of course, useful when you do modeling. You can go beyond this, but you know, that's a nice thing to work with, because then you at least you have one parameter less to play around, or more parameter less to play around in your simulations. And then we then did a study like this in 2023 with Phil, Karsten, Eleonora, William, to study these constant neutrino dark matter interactions in light of this data set at that time. So it was ACTDR4, BOSS for BAO, and the Planck data set. And then we found a mild preference, about 1 sigma, towards non-zero values of these interactions, which was for the values of this U parameter around 10 to the minus 4. You see also the how it looks compared to the fraction of dark matter, basically, of this interacting dark matter. And then what we were happy about, of course, is that, first of all, that there is a hint. It's not very strong. It was at that time consistent with previous hints in Lyman alpha data from 2021 by Diana Hooper and Matteo Luca, almost at a very similar value of the U parameter. And then later on, Eleonora, William, And Karsten also studied this for extending it to ACT-DR6 lensing, SPT3G, and studying the impact of the neutrino mass. And basically, they found a similar, I believe, preference at that time for the neutrino, non-zero, non-vanishing neutrino dark matter interaction. So that was like an entry point for our studies a few years ago. Then we updated this in a paper that we put out first in the January of 2025. It was eventually published in Nature Astronomy. Again, studied this constant cross-section case for the neutrino dark matter interactions, but now we updated it using also weak lensing data, DSY3 at that time. Nonlinear scales were treated with some n-body simulations, basically a grid of n-body simulations that we interpolated between them. And by doing so, in this 2025, we found a combined preference for non-vanishing value of this parameter around 3 sigma. So basically, the significance became larger, sort of. And again, it pointed to the values around 10 to the minus 4, let's say 4-ish of this U parameter. And in the very same paper, we also showed that this effect allows to ease the S8 tension. That was very relevant at that time. I believe it's still relevant. I know the status is changing, but I believe it's still there. And importantly, in this plot, you see we are able to lower down the value of the S8 in Planck and DES, make them agree. Importantly, our likelihood in this analysis is not driven by S8, like we don't have any term, the likelihood that drives the S8 value is just driven by this data, and then as a bonus, so that we get this S8 suppression and potentially alleviation of the tension. So, so now there's a preliminary result, so not yet something that is put out. So we go further, of course, because in opposite to the field that I come from, which is collider physics, cosmology is full of data. So before we publish one paper, there's another data that is, ready to work on. So then we do this with Planck, ACT-DR6 full data set, SPT, and DESI-BAO. And then after doing so, we seem to find a combined preference, which is around 2 sigma, so a bit less than before, without DES, now without weak lensing. But it's stronger than it was before, just based on CMB and BAO data. This is preliminary plot. You see the value of the U shifted a bit towards maybe between 10 to minus 5, 10 to minus 6. It's a preliminary again, so it's still under debate. I'm not sure if you see, but basically, conclusion of all these studies was that we seem to be finding a preference at the level of 2 to 3 sigma for non-zero value of the interaction between neutrino dark matter interactions in CMB and weak lensing that points to the value of this parameter that is at the level of 10 to minus 6 to 10 to minus 5. So that's nice, of course, like discovery, curious face, you can see here. But then, of course, what we need to face are other bounds, eventually, right? So now you see not less happy face. So when you think about how it connects to other cosmological and astrophysical data, then there are multiple ways in which you can also constrain neutrino dark matter interactions. Among them, there is an updated study on the Lyman alpha, I believe, with Julien, probably, and also the study that goes into even smaller scales that counts the number of Milky Way satellites, basically, and bounds the neutrino dark matter interactions based on these. And then eventually there are bounds from the astrophysics, and these kind of bounds, they come, for instance, from the fact that you can emit high energy neutrinos in AGNs, like active galactic nuclei, and they need to go through the dark matter spike. There's dark matter spike, so if there is a huge neutrino dark matter interactions there, then you attenuate this flux of neutrinos, and you should not see these neutrinos while you see them in IceCube, for instance. So there are bounds on neutrino dark matter interactions coming from these as well. So combined, this gives a value, a bound on this constant new U parameter that describes the interaction strength between neutrinos and dark matter that is at the level of 10 to minus 8, roughly speaking. I believe it, of course, up to some prefactors here. So you see, of course, there is a bit of mismatch between what we find as a preference in these cosmological data sets that we were studying versus these smaller scale probes and astrophysical probes that seem to rule out these values. So in order to address this further, at least try to address, we need to go beyond this approximation and actually try to look at this approximation of the constant value of the neutrino dark matter interaction rate, sort of. So this parameter U, what it encodes specifically is the mass of dark matter, but the most importantly, it encodes the energy dependence of the neutrino interaction cross-section with dark matter. So if you try to look at how it works at the microscopic level, so from the particle physics perspective, then I borrowed this nice table from this paper. So the picture that we have in mind is this dark matter particle scattering of neutrino via some mediator particle, and then you have neutrino and dark matter in the final state again. So then you can try to describe it in the effective level, let's say. So there is neutrino, there's some kind of dark matter particle, some kind of mediator, nothing else. You just simplify this as much as possible just to describe the effective interaction that you're interested in. So when you go through this table, then you see they provide the annihilation cross-section and the scattering cross-section that we are interested in between neutrino and dark matter. And this parameter, Y, I'm not sure if you can see it, it's maybe too small, but basically what is important, it's proportional to the neutrino energy. And basically all these cross-sections here are either proportional to the square of this parameter or to the fourth power of this parameter. This means that translating this to the U parameter between neutrino and dark matter cross-section, it is natural to assume that the cross-section between neutrino and dark matter is not constant in energy. It depends as a square of the temperature or as a fourth power of the temperature, at least in most these effective field theories. Of course, we can also constrain these kind of interactions, but I believe this has been done also by William and so on. The results are not that good, so we would like to really stick to this constant cross-section picture. And the question is, can we reconcile this constant cross-section picture, temperature independent, from this? And the answer is that basically the only way, at least that I could thought about, there are two ways, sorry, to do this. So one way is when there is vector mediator, in some cases here, you basically have a constant cross-section at the very high energy, it flattens out. But that's not what you want to do, because we want to have a constant cross-section close to recombination, let's say, which is much lower energy. So that's not what we want to achieve. So the other thing that one can do to make these effective models having a flat cross-section energy independent is to make the mass of neutrino and dark matter, the mass of dark matter and the mediator particle, so this dark matter and the mediator particle, very close to each other, mass degenerate. And then basically in most of these models, you can find a regime of energies. It's not absolute in all energies, but there is a regime of energies in which this cross-section becomes flat. I'm gonna work, in a different example because you see the Lagrangians here of these models. The problem with these Lagrangians, most of them, is that they do not respect standard model gauge structure. So I wanted to go to a bit more sophisticated scenario that tries to rescue these. The problem is that you either, if you have dark matter coupling to these left-handed neutrinos, you either assume there is also a coupling to charged leptons, and that would induce much stronger bounds than any neutrino dark matter interactions that you can have in mind, or you break gauge invariance, which is also not good, right? But there is a way to go. So there is a simple kind of a toy model that is just a bit more sophisticated than the ones that I've just was talking about, in which you have this standard model multiplet that connects to dark matter. But first it connects via a sterile neutrino state. So a heavier neutrino that can have a mass of, let's say, 100 MeV or something. It's not relevant to cosmology, but it's there basically to mix with active neutrinos via this Yukawa-like interaction. And it's this guy, this sterile neutrino, that talks to dark matter. And then to make it consistent, you need to introduce additional mediator particles, some scalar in our case. If this is fermion, then make this scalar. And it's the very same picture to these effective models that I was just talking about, but it's safe from point of view of SM gauge invariance. And it's also safer from point of view of other bounds, in a sense. But the general picture is very similar. So now again, you have basically dark matter. Eventually, it's going to talk to the neutrino, but via mass mixing of this heavy strial neutrino, right? So when you calculate the cross section in this model for neutrino dark matter interactions, you reconvene the same picture as in the effective models. So basically, the cross section is typically temperature square dependent, and no fancy story. But then you go to this mass degenerate regime between dark matter and the scalar field. And when you do so, so here I put so I have this interaction in mind, neutrino, dark matter via this scalar. This is the cross section, which is has some form, doesn't really matter. But what's important, if I go to the mass degenerate regime, when the scalar and the dark matter mass are very similar, then this term here in the denominator basically vanish. If my energy is large enough so that I just introduce this for regularization so that entire thing doesn't blow up, but it's very small. So if the energy of neutrino is large enough, this can be neglected. And then you can see the energy of neutrino here. I just have square of energy because this is negligible, and square of energy here. They cancel, and I effectively get a constant cross section in a range of energies. It's not everywhere. It's just in a range of energies. So you see here the plot. This is this parameter U, and the temperature, the neutrino temperature. So basically the early universe is here, the late universe is here. You see that the cross section first grows, then it flattens to some value. Let's say I follow this line. Then there is this peak that I will talk in a moment, and then it goes back again. But you can make these parameters such that it becomes flat essentially at some time before recombination and is flat until recombination. So that's what you want to achieve if you want to play with constant cross-section and your cosmology in your models. So, okay, hooray, we can do this, and then we can come back to our issue with the with our cosmological hints of these non-zero dark matter interactions. But then we also face the problems with small scale bounds and so on. It's the same story, right? But what is important in this picture, which I think has been overlooked, I also had a chance to talk about this with Celine Bem at some stage, and she actually pointed me to her paper in 2002, I believe, in which she did discuss this. You see, these plots, in all cases, they have these bumps here, right? So where does this bump come from? And whether it's like a feature of this model or it's a generic thing. So the point is that if you want to flatten the cross-section and make these simple sort of cosmological simulations better grounded in particle physics, then you need to go to this mass degenerate regime. But when you go to the mass degenerate regime, there is certain neutrino energy at which you hit the resonance, and basically neutrinos has precisely enough energy when interacting with dark matter to produce on-shell scalar here, this mediator particle. It can be also, it's the same story for other effective models, so it's not specific to this one. And in this energy, the cross-section blows up by orders of magnitude compared to the normal one. So this feature is there, it's inevitable in a sense. If you want to flatten your cross-section by making this mass degenerate stuff, you need to always end up, and fortunately or unfortunately, it always happens at the lowest temperatures here, so at the end, so let's say close to recombination, this blowing up happens. So it's not something that you can neglect in your cosmological simulations, but as far as I know, so far it has been actually neglected. So I talked to Celine, actually, she told me that, she showed me in her paper that they discussed this actually, but they just disregard as a small, bump that doesn't count. But the point is that what I'm trying to show is that this is not something that should be disregarded because it completely changes the picture. All right. So how this resonance shows up? So in this expression again, so you can imagine I can have neutrino energy such that I make this entire bracket close to zero. There is some specific neutrino energy, and if this is the case, then the cross section basically blows up because it's just regulated by this tiny decay width of the scalar here, which can be very small. It's also proportional to the fourth power of the g, so the value of this cross section, this g to the fourth, will cancel. So it will not depend on the coupling. That's another fancy thing. So we will have the cross section that does not depend on the coupling. And basically what you get a peak, which is, as you see, just a constant value, and you need to make sure only that it makes sense, so it cannot blow to infinity, basically. So there's some unitarity cap, you need to cap it at some stage. So now what happened? You imagine you evolve the universe from these large neutrino energies to the low neutrino energies, and then first the interaction is very, very small. Then there is this flat part that you like because all your cosmological simulation treat it, and that's what you are doing basically. And then there is this boom, big thing that blows up, which has not been treated before, and then again it goes down, so it becomes irrelevant basically. Okay, sorry, that's just a message that this resonance is kind of inevitable in this picture. To make it like with AI, sorry, it's hard to make I can talk today without using AI for anything, so at least this thing. So again, to make it more pictorial, basically you can imagine that the universe evolves. You start with high neutrino energies, and then the universe expands, so the neutrino temperature drops down, which means that neutrinos have Fermi-Dirac distribution, but so this is more like a Gaussian, but it's just AI didn't make proper Fermi. But basically the point is that when the neutrino drops down, at some stage you start hitting this resonance, and then there is a peak moment of doing so, and then you go to even lower energies, and then you don't feel the resonance at all. So the point is that even though the resonance here in this temperature or the energy of neutrino is just a narrow thing, just a very small thing, it will affect the cross sections at a wide range of redshifts because of this effect. First, it's going to be a small effect, then increasingly large, and then again, smaller effect. Okay, how to model this small technical thing, but I believe not too much. So basically, this you studied. I didn't have to go in this. At least I didn't go in these studies into any Boltzmann hierarchy. Just studied this at the level of modified evolution of the fluid velocity divergence. So this would be a normal thing here, and then this term introduces the neutrino dark matter interactions, which is a standard thing in this literature. And then essentially it has this interaction thing here. Sorry, this chi should be a small subscript here. And then how you can calculate this, basically I use the ethos formalism. We convolute the momentum transfer kernel, which is this A0 thing, with the unperturbed Fermi-Dirac distribution for neutrinos. We assume that these interactions do not change this distribution, which is of course another assumption. I will come back to this at the very end of my talk. And then this kernel, it's some function, but basically it depends on the invariant matrix element of the neutrino dark matter interaction. So I change the model, I plug in different invariant matrix elements here, then I plug this in here, and then I calculate this this quantity, and then I can plug it to the modified evolution of fluid velocity divergence. And in principle, I can also plug the invariant matrix element that contains this peak and the blow up of the cross section. So when I do so, I end up with this picture. So it's a bit busy plot, but this is again this U parameter. I define it here. So you see there is the cross section of neutrino dark matter normalized to the Thomson scattering cross section, which I believe is just as standard literature thing to do. There is also dark matter mass, and then there is a redshift here and the neutrino temperature. So we start with high redshift, and then we evolve the universe to lower and lower things. So if I neglect the convolution and the fact that neutrino has energy distribution which changes over time, then my picture will be very simple. I would have a flat cross section and then a peak, and it goes down. So that's basically that's basically this picture that I show you here. But if I convolute it properly with this Fermi-Dirac distribution and so on, then the neutrino dark matter interaction, you see it behaves like this red term, the red dashed line, which is called thermally averaged. So basically it is very low at some high redshift, then it grows to large values at the redshift range, and then it becomes very, very small again. So it's basically, it's not, importantly, it's not flat and it's not t-square. It's something sort of in between, as dictated by this resonance structure. But again, as I said, it's kind of inevitable if you want to have this flat cross section, because at some high redshift there will be a flat cross section again. Okay, so how does it impact? So eventually you see that what it does, the neutrino dark matter interactions, they blow up and enter at some redshift range. So not at very early universe, not a late universe, at some redshift range that could be prior to recombination. Sorry. So in terms of cosmology, so here is the shaky ground for me I'm trying to explore. So when we think about perturbation evolution, then we can think about, I think, in terms of large scales, intermediate scales, and small scales. So by large scales, I mean the perturbations that enter the horizon after the neutrino cross section cease to be effective. Sorry, so somewhere here in this plot, let's say, in which case, if this is after, they feel nothing about neutrino dark matter interactions that were active before, and basically they behave like standard models. So here's the transfer function. You have basically something like lambda CDM. Then if I go to really small scales, they enter the horizon before the neutrino dark matter interactions became effective. So in this place, this will be somewhere here before this thermal average blowed up. In this case, they will, of course, feel the effect of this, which happens later on. Depending on when they enter the horizon, they will have more or less time to grow as the perturbation before the neutrino dark matter interaction starts to be effective. But eventually, what it happens to them, they feel this effect as a kind of integrated effect. So what you find is that this integrated effect, it does not depend that much whether the perturbation entered the horizon here or here or here. So the transfer function kind of flattens out. It's not precisely flattening. It grows a bit, but it kind of flattens out. And then at intermediate scales, there is a moment in which these perturbations enter the horizon precisely at the moment when neutrino dark matter interactions become effective. And this is the moment when we have dark acoustic oscillations, large damping of the power spectrum, and all the effects that are fancy from cosmological point of view. All right, so how does it look in practice? So here are some points from our analysis that, I don't think I need to really describe what they mean, but what's important, you basically see this picture here in some of these parameters, some of these plots. This is the transfer function, so the power spectrum versus the lambda CDM1. So you see at really large scales, we reconvene the lambda CDM picture. Then there is a strong suppression at some scales, which is for us, it was the relevant values were around 1, K around 1. And then for smaller scales, you see there is this flattening happening. So the power spectrum grows again. So the smaller scale will become less and less affected eventually. This is the linear power spectrum, of course, so here the nonlinear effects will enter eventually. And here is another plot that explores more benchmarks for these, and you can see the same picture. You can make it deeper or less deep, basically, and make the flattening also like lower or very close to lambda CDM, such that you can localize your interaction really very close to these scales that are relevant, let's say, for the weak cleansing analysis. All right, so once you do so, then you can try to test it again with cosmological data. And that's what we did, of course, with this data set, which is ACTDR6, SPT, DESI, and also with KITS legacy, with some question mark on this, let's say. And then by doing so, we find in this picture of this resonant, kind of resonantly enhanced cross-section, we find again the 3 sigma preference for non-vanishing value of this interaction strength. You see now this U parameter is shifted even more to larger values, but important thing is that it's well localized to be around 10 to the 5, the redshift 10 to the 5, which means that it's very small at larger redshifts and very small at smaller and smaller redshifts, you make these, sorry, just coming back to this plot, you make this red thing narrower by playing with the parameters and really localize around 10 to the 5. That's what happens. And by doing so, you see this the posterior plot for this U. So by narrowing down the interaction, of course, you require a larger interaction strength to make the same cosmological effect. But what is important, again, one thing is that, generally speaking, is a more realistic picture than just a constant cross-section, because there is this resonant effect that has been overlooked before. And then another thing is that there is more flexibility to avoid bounds at different scales. And the reason for this is basically such that we can localize this and do not affect that much smaller scales and also, of course, larger scales, as I discussed before. Okay. So that was about cosmology. And then I go back to something that is more, let's say, easy for me to talk about. And then at this conference, I thought, especially this week, I thought I should tell something about scalar fields. So there is here I go, right? There is connection to scalar fields. So now you can think, okay, so I'm talking about these small mass degeneracies because I wanted to have this flat cross section, and then there is this resonance, blah blah, right? But then, okay, does it even make sense to consider these small mass degeneracies, right, between states in the dark sector, right? So one thing that can work for this is, of course, you can have them symmetry protected. So small mass splittings between things in the dark sector can just happen, for instance, if they come from the same super or multiplet, let's say, and then they are naturally at the same mass scale. That's nice. Then, of course, there are always radiative corrections to this, and these radiative corrections can naturally be larger than very tiny mass splittings that we want to achieve in to study the CMB close to recombination. And because of this, typically in such cases, the fine-tuning appears. To give you an example, the model that I was talking about with this sterile neutrino and dark matter and so on, if I make the mediator and the dark matter very close in mass, just by hand, let's say, at high energy, assuming that they might be coming from the same super multiplet in the more UV complete case, then radiative corrections will bring the mass difference between them to about, let's say, mega electronvolt scale. So it's above what I would like to have to be around, let's say, electronvolt scale to be able to fit the CMB data. So either I fine-tune the initial masses so that the radiative basically makes them the same, or maybe I can do something else. So one thing that we also discussed in the paper that I was mentioning is some sort of dynamical mass degeneracy. So I think I probably do not need to convince anyone in this room that if we have a background scalar field, it can couple to matter. And when it does so, it can also impact the mass of the matter species and basically make them field dependent and make them, dependent on time in this case. So here I just put one example from this paper by Pratek Agrawal, George Rubiet, and Kumbun Wafa about the quintessence-like scalar field that shows the mass dependence that can be basically of the field that goes exponentially as the values of the field. So over time, basically the masses go down. And then it's very natural to assume that they can also behave differently for different things in the dark sector. But other examples were given also in this conference. I believe Anne, Karsten were talking about some examples of such scenarios. So the picture that we have in mind is that there is this dark matter and there's maybe some mediator. They are close in mass, but not very close. But then thanks to this coupling to the underlying sector, you can actually make them both going down such that they eventually become, the difference between them becomes smaller and smaller. So they can naturally hit the resonance kind of dynamically. One nice thing is about this is that we are sensitive here, going back to this toy model that I was using, we are sensitive to the changes. Let's say my dark matter mass can be GeV or so, and the mass splitting to begin with can be mega electronvolt, so at least 10 to minus 3 or less. So these kind of shifts in mass can make these two masses very close to each other, and can have a dramatic impact on cosmology. So cosmology and these resonances in the dark sector, let's say, could be a way to reveal the underlying scalar evolution and dynamics beyond what is really achievable in normal cases, let's say, by just making them very, very close to each other. So I use even my Tor model just for illustration. So basically, I just assume a scalar potential here and this kind of mass splitting. So I assume that I actually had some fine tuning maybe in the early universe, very degenerate masses. So degenerate, there was no effect of resonance in the early universe because the neutrino energy was too large, basically, to see this. But at some stage, this evolving scalar field that actually would start oscillating in this simple toy model starts to diverge these two masses so that the difference mass difference between them grows, and if it grows, then naturally at some stage it can cross the proper value that hits the resonance of the neutrino interactions. So in this picture you see this is this blue curve MK tau here, which is much narrower than the red one. And by playing more with these resonant dynamical changes in the masses, you can make it even much more localized on time. So that's the thing that can make our interactions really effective only in a certain cosmological epoch, and can also potentially reveal the dynamics of this background field that is at the level, like the mass change is at the level of 1,000, right? So that's nothing, like, you cannot really measure it in any way for dark matter mass change of 1,000. But if there are these resonant, like close in mass dark sectors, then this 1,000 mass can have dramatic impact on cosmological stuff. All right. What time? How much time do I have? 5 minutes. Okay, so I'm almost done. So there are other tests, like, of course, for this, but maybe this is a bit less relevant for the conference here, but basically, depending on how large is this mass splitting, in the MeV range, we can use supernovae neutrinos. In the GeV range, you can go back to these high-energy astrophysical neutrinos and neutrinos traversing through the dark matter spike. But below mega electronvolts, it's very challenging, and here is basically cosmology to the rescue. And then there can be independent bounds on these from dark matter self-scatterings and small-scale structure, because you can induce basically dark matter self-interactions if there is a closely mass degenerate mediator. What I wanted to highlight maybe in the last 2 minutes, let's say, there are other effects that I have not studied yet, but I believe could be worth discussing. So one thing is that when you have this resonance and your interaction blows up at a certain cosmological epoch, then I was just focusing on what happens to dark matter, basically, in this case. But obviously, you can imagine that when the interaction becomes very large, then this also will induce neutrino dumping. So basically, the neutrino free streaming will be frozen for a short period of time. So this kind of stuff can give more space for additional delta N effective produced at earlier times if we later kind of freeze the free streaming of neutrinos. And this has been studied in the context of the H-naught tension and these Majoron kind of models in these papers. I know that probably Eleonora will say that it doesn't make sense at the end, but at least from the particle perspective, this has been discussed as a possible alternative. And these resonant interactions give naturally this suppression of the neutrino free streaming at just a certain epoch. And then if we go to these underlying scalars, then if we have these two dark states, then I think one thing which is very much more general than neutrino dark matter interactions, one thing that has not been maybe explored, at least I'm not sure if it was, is that if we have a dark matter state and then some heavier state, a bit heavier, not much heavier, and then they both evolve with this background field, but differently, then you can imagine easily the situation at some stage in the cosmological evolution, this guy, let's say, drops more than this, and eventually they cross. So what happens if this happens? if it's the case, then the identity of dark matter changes, you see, because of course dark matter needs to be the lightest one, typically, because the heavier one, this, will then decay to the lighter and emit additional radiation. So there are at least two different effects that can be associated with this. One effect is that in this decay of this guy to this, you will basically produce a bit of heating of the universe. It's not much because this guy will likely decay very close here, so not much large mass splitting, but there will be, you can probably make it larger, depending on what you want to achieve. There will be a bit of heating to the universe to this. And then the other thing, from point of view of particle physics perspective, is that you completely lose track of the connection between dark matter behavior in the early universe and the late universe, because it's just a different thing now. And then if you search for dark matters, especially in this thermal production paradigm, then one of the most important things is to search for dark matter annihilations, maybe in the galactic center and other objects like dwarf galaxies. And this relies on the connection between what we know about the dark matter production in this thermal paradigm and the relic density, the cross-section that was there, basically, and the late time annihilation cross-section. So, and then we have bounds on these and so on. But in this picture, you can ease most of these bounds, likely, because basically the connection completely lost. And this guy, for instance, can have much suppressed annihilations today by, for instance, velocity suppression and so on, which this guy originally didn't have. So that's something that I think, you know, background scalar fields connected to dark matter could potentially, you know, give a nice phenom for this. All right, so here's my summary. Sorry if I went, it's probably okay time, right. So neutrino dark matter, I believe, still exciting opportunity. There are hints of non-zero such interactions in high multiple CMB and recleansing. There are bounds, of course, that one needs to keep in mind. And then what I was trying to convince you in this talk is that how people model this with the constant neutrino dark matter interaction requires a bit of a upgrade, sort of, because if you go to this and try to put it in the context of more realistic particle physics setups, then this requires compressed mass spectra. But when you go to compressed mass spectra, then you naturally end up also facing resonant effects that will affect the entire picture also for the cosmology. And then I was discussing a bit this coupling to the background scalar field and mass variation and some nice effects that it could do on the dark matter identity and other stuff. Okay, thank you very much.
Thank you. Questions?
Yeah, thank you. It was amazing. I've written plenty of questions, but I will only ask two now. So for the effect of the resonance on the matter power spectrum, you explained that there is a deep on intermediate scale, but the very small scales are not too much affected. And you said it's because when there is this strong coupling regime, there are some dark oscillation, but at the end they get averaged out and you don't see any effects on the net growth. And it sounds completely reasonable. Another thing that would have sounded reasonable to me a priori would be to say, oh, during this stage, there is strong collisional damping for dark matter. It has a very small mean free path. And because to this diffusion or collisional damping, the dark matter fluctuation get completely erased and they will never recover. So your simulation show that it's a first explanation, which is correct, but do you understand why it's a better explanation than my hint? Yeah.
Well, this goes to this part of cosmology that, you know, I'm not that much expert. I would actually be very happy to talk to you if you, but the point is that, so yeah, I think, you know, the effect, as you said, I believe it's averaged out sort of, but yeah, I probably need to,
yeah. But so this comes out from the simulation you did, which is Probably it's Boltzmann code. No, it's linear level.
Yeah,
Yeah.
yeah. It's a linear level.
Yeah.
Although when we do this analysis, we add this Kids legacy. So there is also the nonlinear part later on, which is n-body grid. So it's a bit simplified.
Yeah,
I would say,
but in the previous slide that you just flashed, so the fact that the power spectrum goes up again at large K, this is what you get from class, not from n-body.
Yes, this is the class.
So it's very rare to see this and very interesting. And so you got consistently this 3 sigma preference for the interacting neutrino, both from the old papers without the resonance and from the recent paper with the resonance. And can you be a bit more specific on which data drives this? You said TMB high multiples and weak lensing.
Yeah.
Regarding the weak lensing, is it still true when you take into account that the new kids data does not have an S8 tension anymore?
Yeah. So for the S8 in this analysis, this is the one with the resonance sort of. So the S8 values here are at the level of I believe sorry, where do I have this? At the level of 0.8 or something, so kind of consistent with kids and consistent with Planck and so on. It's no fancy story. We didn't really touch upon this on the paper in the paper, and I believe this. Sorry for jumping, but in this early analysis, like this one, I think that the preference was driven by high multiple CMB, so basically by ACT, I guess, right? Yeah. And then in this combined paper, which is still about the constant, there was also a bit of preference by the weak lensing from DES, and then the combined one gave a 3 sigma. Now, when we go to this resonant picture here, then I think that the kids actually has more to say than ACT, because especially ACT DR6, you know, they change, right? They're much more expert than me in this, right?
They have a lot of power on small scales, while your model is suppressing power. It's not very intuitive.
Right. So in this fit, I believe the kids has more important impact on this thing that we find. But
Okay.
So that's the
Thank you.
Right.
Any more questions?
I guess it's too niche.
No, you mentioned bound from Ice Cube. I was completely unaware of this. Sounds very interesting. Can you summarize what's going on there?
Right. So there is a bunch of papers discussing this for different blazars and AGNs. But to be honest, I believe that these bounds, okay, there are some of them like NGC that are quite strong, but some of them are not that competitive with this Lyman alpha here is not your work. Not the latest paper that you put out. So I think your latest is probably better than these guys. But basically the story here is such that, you know, IceCube observes these very high energy neutrinos, right? And they try to associate with some astrophysical sources like active galactic nuclei and so on. So there is a big astrophysical assumption behind these bounds such that when you have this AGN, there should be a dark matter spike around it. So when you produce neutrinos close to this AGN, then it should traverse this spike before going to the space and eventually reaching the Earth. So now if there is this dark matter spike, I mean in density, there is a lot of dark matter there, so a lot of chance for interaction. So if your interaction cross-section is too large, then you attenuate. So many of these neutrinos will interact, and you will attenuate this flux. And there is another big assumption behind this, is that you understand how many neutrinos should be produced. And this you can kind of understand because if I go to this picture, which is just a fancy graphics, but the real thing that happens is that you produce, for instance, proton jets, in this AGN. And then these protons interact and they produce pions, for instance. These pions decay, they produce eventually neutrinos. But then on top of these, there is also photons that are produced here. So by studying these photons, you can deduce something about the original proton jet, and then you can deduce a predicted neutrino spectrum. And then you have a predicted spectrum, you see what you measure, and you compare, and if there was a bump, you can say, okay, the cross-section is, but if there is no bump, they more or less agree, and then there is a bound on the cross-section.
Okay.
But what is important, of course, is that this is for really high energies of neutrinos. So if you have a model that has this resonant cross-section and so on, in this picture that I'm completely lost now in my slides. Okay, this would be somewhere here in this plot. So the cross-section might be very, very suppressed in many models.
Okay.
Yeah, if you go, right. Yeah.
Maybe a last one. When you discussed all the possible coupling terms in the EFT approach, what is the reason for showing also here this diagram of inelastic scattering rather than an elastic scattering diagram where you would have a neutrino line, a dark matter line, and just a vertical boson in between?
Well, so this is elastic. If you see, this is dark matter, neutrino. There is a mediator particle. You can make it, depending on the model. But okay, in this picture, in this picture, the couplings are organized such that there is both S channel and U channel contribution, actually, the cross section. I focus just on the S channel because the S channel is the one that eventually has this resonance. But that's elastic scattering. So there's neutrino, dark matter in the final state. You go from left to right. Maybe that's confusing. Via this mediator. So that's elastic scattering, not inelastic. I'm not sure what was your...
Okay. No, but because when you write Thomson scattering between electrons and... I mean, my question is just why don't you write a neutrino line from left to right, a dark matter line from left to right, and they would just exchange a boson in the middle?
No, you can, of course. I mean, that's the structure of this model, but you could, in this model, you have effectively this coupling between neutrino, dark matter, and the mediator. So that's why you need to have this vertex. So you mean something like this?
Yes.
Neutrino, dark matter.
Yes, precisely. Yes.
Right. So for this, you need to have coupling between neutrino and the mediator. And dark matter and the mediator. It is possible in different setups, sort of. But in this case, in most effective models, you will again end up with this T-square dependence. But there will be this is T channel or U channel, so there is no resonance. So basically, it's not easy to make it flat in any regime. So but if you go to this kind of picture, here we have couplings, because the issue was that in this plot, you see that there are couplings between dark matter and neutrinos and the mediator. So the coupling is like this, neutrino with mediator. So there are no such vertices. You need to write it this way. Like that, right? And that's the model that I discussed is just a tiny variation on this to make.
So they are both possible, but this kind of diagram is phenomenologically more interesting.
Right. I would say so, but of course, if you just write it like here, then there are problems with this SM gauge imbalance. So you need to go to this. But this could, in principle, be possible, of course. And then there are. You can also imagine that then, if phi couples to neutrinos, then there will be bounds from neutrino self interactions, because you can also just have neutrinos here then. And there are bounds from cosmology on neutrino self scatterings. That's yet a completely different story. But
yes.
Okay,
fantastic. Thank you.
Thanks.
Any more questions?
Thanks for nice talk. I have two naive questions. The first one is when you test your model, this intact in that dark matter and neutrino model, and to give the feed for the CMB lensing data and the other Cosmo data. Did you compare the like chi-square with the Llama CDM to see like if this model preferred? or not?
Yeah. So I don't have these numbers here, I think, and the fee. Do I have the? Sorry. Right. Right. But basically, yeah, I mean, we did, of course, there is a preference. So that's why we also end up with talking about 1 sigma, 2 sigma, blah, blah stuff. But I don't have the numbers in mind. Sorry.
Okay. Yeah,
Yeah.
so you said your model is like better than
Yeah, I mean, it's not 5 sigma, right? It's just some preference, right? It's
okay,
not,
yeah.
right.
And the second question is when you talk about this resonance
Right.
interaction model. Did you like? I just wonder like how the mass of the neutrino, like when they play the role in this model.
Right. Okay. So that's a very good question, actually. So I'm typically working in the massless neutrino regime, which is of course approximation. But the point is that from studies, I think William, you did study about this, right? And I think that if you include neutrino masses, then you might shift the best fit value of U maybe a bit, but the preference kind of survived. And that was also noted in the past in some Lyman alpha paper. And the issue is that in this picture, if I talk about 10 to 5, for instance, because that was the one that I was focusing eventually, the redshift, then the neutrino energies are still like at the level of 10 electronvolts and so on. So they are highly relativistic in this regime. So the impact of neutrino mass is kind of limited on this data.